Hello and welcome to our Ship and Offshore webinar powered by MTU. My name is Katrin Lau. I'm the Deputy Editor-in-Chief of the International Maritime Trade publications Schiff und Hafen and Ship and Offshore. Today's webinar will provide you with some first-hand information about Power-to-X technologies and their opportunities for a decarbonized shipping industry of the future. We're very happy that two experts in this field will share their knowledge in a compact format with you. And before we start, here is some housekeeping. I hope you can all hear and see us all right. You will be able to raise questions via the question button in the panel on your screen, but only by typing them in. All participants of this webinar are muted. Questions will be selected and answered at the end of this webcast, and questions that are not being answered today will be addressed afterwards. After the webinar, you will receive a link to the recorded session. And now it is my pleasure to introduce our two speakers of today. We will start with Dr. Daniel Chatterjee, who is Director Technology, Management and Regulatory Affairs and Head of the Green and High-Tech Program of Rolls-Royce Power Systems, Germany. In the new organizational unit Power Lab of Rolls-Royce Power Systems, Daniel oversees technology management and regulatory affairs. Our second speaker, Stefan Müller, is Director Application Center Marine and Naval at Rolls-Royce Power Systems, Germany. He joined MTU Friedrichshafen in November 1989. 2002, he took the responsibility of the Department New Technologies and Design Studies. And in 2006, he started in his current position. But now, Mr. Chatterjee, over to you, please.
Thank you, Mrs. Lau. So a warm welcome from my side. It's my pleasure together with Stefan Müller to give you some insights in, I would say, very exciting topic and I think very important topic, Power to X. So with that, we just start. I think one of the main challenges, besides clearly COVID currently, we have as a society, but at the end also as a maritime industry, is the quest how to get to climate-friendly, climate-neutral shipping. And at the end, what is our role? You see here on the screen that we basically emit every year 36 gigatons CO2, just at the end by burning fuels. And major part is from power generation, boat transport, but nevertheless, we have 2% air transport and 4% is maritime and rail transport. Maritime itself, it's up to 2 to 3%. So, and to achieve really climate neutrality, it's clear that all sectors need to decarbonize. And so that also brings the challenge also to us in the maritime industry. The challenge is even more pronounced if we just take into account, like you see on that chart, that the emissions of CO2 of the maritime industry of shipping will increase because global trade will increase. Nevertheless, we have COVID, but on a larger scale up to 2050, larger time scale, it will increase, and by that the CO2 emission will increase. And therefore, the challenge is with increasing CO2 emissions to come to a reduction. And basically, I think most of you are aware of the IMO 2050 goals, so to have a reduction at least in total of 50%. And a lot of from our customers, stakeholders in the maritime industry, they have even more ambitious targets to reduce even further and maybe in an earlier time. So the blue part of that graph just shows you what, or the graph shows you what options we have. And the blue one is basically the estimate what we can achieve with optimizing the current technology options we know. The orange one is the potential we have by operational measures, so just operating our ships and fleet more efficiently. And that two options, they will basically dampen the increase, but it will not bring us enough reduction to really have a total reduction. And that's where the green part comes into, where we will need new and innovative measures, and especially, and I think the major part will be fuels to achieve the significant reduction of CO2 in the shipping industry. And that's also the reason at Rolls-Royce we have set up, we call it a green high-tech program, where we say, what are the technologies where we need to work on? And basically we invest 500 million euros of the next 10 years to transform our portfolio, provide solutions for our customers to help them to have a CO2 reduction in their ships. And that's basically efficiency. So even the engines we will need for the next coming years to increase their efficiency in regarding CO2 and emissions, electrifications, for example, via hybrid, digitalization and system integration. And one major part, and that's where we want to talk today, is alternative fuels. And we believe the picture regarding CO2 at the end we need to have is really, we need to start with the energy source. So most of the time we talk about what is the right energy conversion, is a combustion engine the right one or some other alternative. We believe we need to look at the whole picture, and that starts with the energy source. Next, the energy carrier, which is basically the fuel, the energy conversion, which then brings us to propulsion. And if we have in that chain, if we have no CO2, that's clearly we are CO2 free. The other option is if we have, for example, energy carrier with CO2 and burn, for example, it is a fuel to take back the CO2 in the cycle. And by that, we would be also CO2 neutral. That would be the other option. And that brings me to what we call the color code of energy and fuels. You might heard already of blue, green, or turquoise, hydrogen. And that's a quite general principle. So if the origin of the energy is fossil-based, could be coal, could be oil, then it's basically what we call it a gray energy. And basically there is no CO2 reduction, at least not at the origin of energy. And there are different options. So for example, you can take methane and make pyrolysis out of that to produce, for example, hydrogen, and then you have carbon in a solid form, which you can store quite well. And that's turquoise. Then blue would be if you store the CO2. And then you have, in our color code, light green, biogenic based energies. And clearly, if you use renewable energies like photovoltaics or wind energy, that's green, in our color code dark green, because that's really then CO2 neutral. And if you make based on that energy carriers, so fuels, that color code transfers. So clearly, if you have oil-based diesel, that's still gray. And if you produce hydrogen out of methane, like it's done for 95% today of the hydrogen, it's still gray because the basis is not CO2 neutral. And even a battery which is stored by energy coming from a coal plant would be gray because in the process you emit CO2. And you can continue that process. So if you made out of that pyrolysis hydrogen for the ammonia, or you use that hydrogen to store the energy in a battery, the same color applies to the energy carrier. And if you start with renewable energy, and out of that process, we'll explain a bit later, you make diesel, methanol, or the other fuels, it will stay green. And you can also divide the energy carriers in carbon-based fuels, as we know it mainly from today, or carbon-free fuels, which would be in the maritime environment, quite new fuels like hydrogen or ammonia. So that's basically the picture from the fuel side. And if you go now to the energy conversion side, and Stefan will go more deeper into that, that's then basically, in some sense, in that context, a secondary question. I mean, it's an important question, but just from the CO2 perspective, we believe that the combustion engine, it will stay for many years for various reasons, especially for looking on the energy density we have. But clearly that engine today it runs on diesel, and there are a lot of ships now going to gas, but it could also run on hydrogen or methanol, would be just other options. But we believe we will see also new energy conversion technologies like fuel cell. And if you go for on a system level, and that we combine those energy conversion units, for example, in a hybrid configuration with a battery. So these are then all options to also more efficiently convert the energy. And why are e-fuels, which will be produced by Power-to-X, so important for marine, but also for other applications? If you just look on the efficiency, and that's the main critics sometimes you hear about that, direct electrification sounds like the best way. So you start with wind energy, for example, you store it in a battery and use that energy to make your ship propulsion. And the efficiency at the end, it's around 70–90%, which is really good. If you then go the route, you make, for example, hydrogen out of pure wind energy, and you burn it in a combustion engine, you end up with 15 to 40% efficiency. And that sounds not good. And at the end, you will require, at the end, 2 to 5 times more renewable energy. Okay, but why then care about e-fuels? I think the important question is energy density. And that's already one of the main benefits of diesel we have today. If you just take one of our engines with 2 megawatts, you would run it for 8 hours, we would need 100 tons of batteries. I think that shows an example why it would be very difficult for, we call it high power applications like marine, like also aviation, trains, or heavy duty trucks, to just put them directly on electrification, why it's just unrealistic to do this. And therefore we need still fuels, and the question is, if we want to be CO2 neutral, how we get the fuel CO2 neutral. And that brings us to we call it Power-to-X ecosystem. So the Power-to-X process stands for Power to X, so to various fuels. And the origin always, as I explained already, it's renewable energy. So wind and solar. By that, we use that energy in an electrolyzer to produce hydrogen. And that hydrogen, so we call it e-hydrogen because it's derived from electricity. It's actually the first e-fuel. You can use the hydrogen already as a fuel, but there are challenges regarding infrastructure handling. So there are various reasons to go further, and that's the fuel synthesis, so a chemical process where I take for CO2 and you produce out of that hydrogen methanol, e-diesel, e-methane. So new fuels like e-methanol, but also fuels we know like e-diesel or methane could be options. You might now ask, okay, what's the point now? Again, we have CO2, and that's what we want to avoid. And to stay CO2 neutral, that CO2 needs to come from air. The term for that is direct air capturing, can come from biogenic sources. With that, we stay CO2 neutral. Another option would be industrial sources. At least that would be kind of a reuse. And so maybe that picture on that, Patrick, sounds simple, or maybe you guess, yeah, it's a good idea. Why we call it ecosystem at the end, and why it gets sometimes a bit complex, it's a whole ecosystem. Because then if you go in the direction, okay, what kind of fuel to use? Should we use hydrogen? Should we use an e-fuel? Or again, what are the options for use directly electrification? Other option would to use the hydrogen for stationary applications, like for power generation. So in that case, it would be like a storage of renewable energy to produce again. Electricity, you can use also the heat. And so what happens with that, you couple a lot of sectors together, what is not the case we have today. So one simple example, that picture will only work if we have enough renewable energy, otherwise it will not work. Also, it will only work if we have the capability in mobility sector, for example, to use hydrogen or all these e-fuels. So all these sectors play together, and therefore, in our view, it's an ecosystem which we need to understand, and we have to look at the whole ecosystem. So therefore, the value proposition for Power-to-X fuels, there are various ones. So one is clearly by producing those e-fuels, especially if you go for e-diesel, e-methane, we have the option to use the existing infrastructure. And also we can address the existing fleet, which is a great benefit because we need to address the existing fleet to achieve the climate targets. The other way is it's a way to use renewable energy sources even in those applications which require those high energy densities, which cannot directly be electrified. And clearly, green hydrogen is the central ingredient for all that. As I mentioned already, and it's a key for reducing hard to electrify applications, especially marine. Another topic is it will also enable renewable energy imports, because as we will later see, there are a lot of regions where you can have very attractive conditions to produce the fuel. And they have also enough energy from sun and wind, but basically they would not need all energy. Other way, we have maybe in Germany not, for example, not the best conditions to produce all the fuel we need. And nobody from remote areas will bring us to the energy with a power line. But if we transfer the renewable energy into fuel, we can trade it on a global scale. And another good message is we believe by our calculations by 2030, the cost of power-to-X fuels is forecast to be at least cost neutral with biofuels at several locations, which would be another alternative. And to give you a picture of what is the projected amount, how could the ramp up look like? We would like to show you that data. So on the right hand side, you see all the sectors which would need a certain share of the fuels. And the light blue color just show you, it's calculated in energy, what share needs to be CO2 neutral fuel. And clearly in marine, 50%, aviation, 70%, that's clearly areas they have not that much options, and therefore the share is very, very high. For passenger cars, for example, it's 10%, because the majority of passenger cars can be directly electrified. And if we bring that all together, in 2050, we see a demand for those type of CO2 neutral fuels by 20,000 terawatt hours, which is really huge and significant. If we now look maybe in the shorter time scale, there we see also already a need for CO2 neutral fuels, and we believe that need will be matched by biofuels, just because they have already a certain and a significant production capability. But in 2030, from our projection, that would be the range where we see power-to-X fuels coming in a larger scale into the market. And if you also look in that, I think it's also necessary that power-to-X fuels come into the market, because biofuels will be not able to meet the demand, and maybe they should not meet the demand on that larger scale. Because if you look on land use, water use, that's like 20 to 30 times more than for power-to-X fuels. And that would be maybe not the right choice to try to do everything with biofuels. So that, I think, shows the importance of the fuels, gives you a certain time scale where we believe they're on a larger scale there. Clearly in the next year, we will see first pilot projects that will be locally available. That's the way we believe that power-to-X fuel can be ramped up. Next question is what kind of fuels we see, especially for our high-speed engine applications. As I mentioned already, and you see also other sectors out of marine, and that shows you that fuels that will play also a role in other sectors. That for marine, as I mentioned already, we see it in many applications today, biofuels. We have LNG in the form of methane. And then we believe e-diesel, e-methanol, e-methane, and even hydrogen that are attractive fuels we see made by power-to-X. You might heard also of ammonia, and Stefan will explain also on that. We have not put ammonia currently on that roadmap, just because we believe for coastal shipping with a lot of passengers on board, that there's some safety issues which needs to be clarified. But to be honest, we believe that roadmap is a kind of a fluid roadmap. So that's something we need to discuss also with you as other stakeholders, what is really the choice and the most important fuel which will evolve. So that's nothing which can be treated or looked very static. What now to come to one point, as I mentioned already, where are this fuel produced? And for that, it's important to understand that one cost driver clearly of producing those fuels is the electricity cost. On the other hand, if you build up a fuel plant, watch how much full-time operating hours you have. And this map just shows you in a kind of a heat map style the full-time operating hours of a combined photovoltaic and wind power plant. And the red regions, for example, Chile, Patagonia, or in Africa, they can come up to 6,000 operating hours per year. The blue ones, you have more than like 2,000 hours. And that's really one important factor. And I think it's from that it's clear. To give one example, Chile, Patagonia, for example, would be a very attractive region to produce a lot of renewable energy. And I explained already, it would be difficult to have a wire directly to Europe, to Germany, or some other country. So the question is, how can basically this one address that amount of renewable energy? And that brings us that molecules of fuel is maybe a very good idea to come to a global energy harvesting and trade. And to show that at the end, we need to have maybe a different look on efficiency. We have defined, we call it energy harvesting factor. So basically the idea is, just in an example, you have 10 megawatts wind energy. You have it in Germany. You can run usually by 1,800 hours, full-time hours, that windmill, and you end up with 18 gigawatts. If you now stay fully electric, so you have transport by wire, charging, utilization, you can, at the end, you have 30.2 gigawatt hours on propulsion energy, for example. If you would produce hydrogen in Germany, you have all the losses. So you have lower efficiency with electrolyzers, you need to transport it locally, and you have 40–50% efficiency in the combustion engine or even the fuel cell, and you end up at 4.3–6.3 gigawatt hours. And that's sometimes the discussion we have with efficiency. But we believe that we need to have a bit different perspective. If you go for Patagonia, and our 10 megawatt wind plant will run for 6,000 hours. So we have 60 gigawatt hours. And then if you go the same route, we transfer to hydrogen, we have significant transport losses, and we use it in a fuel cell or combustion engine, we end up with 11 or 70 gigawatt hours. And that's really comparable to what if we look at a local energy production in Germany. And even if we go the diesel route, so if we add additional losses to a synthesis, it's still comparable to the electric propulsion in Germany. I think that picture showed if you go more, take into account where are attractive regions, what we have into our energy harvesting factor, it's maybe not as inefficient as it sounds like from the first glance. I think that's an important point to note. One thing also, just a view on cost. What we've shown here are the abatement costs. So if you just replace your diesel as you have it today by synthetic fuels, and clearly our projection that's for Chile, if you produce the fuel in Chile, so it's a kind of a best case in 2030. So there are some learning curves into that picture. What is the price range we expect on different parameters for different fuels? And you see there's an additional abatement cost, so the fuels will stay more expensive than fossil fuels. That's clear. I mean, hydrogen itself can be produced maybe more, comparable to fossil fuels, so that's why it's negative. But I mean, pure hydrogen can be not used as a fuel, so we need to have it in liquefied form, or we can make ammonia, methanol, methane, or e-diesel. And basically, you see there are additional costs, at least of 100 euros per ton CO2, which we want to avoid. And the good message is, if you look for biofuels, we have a same range, and that's why we say it's comparable to biofuels. So if you need to make a choice, so where to go, I mean, you see that's not clearly that you can say, well, that's the cheapest one. It depends really on what conditions you have, where you can produce the fuel, that's within that range. But the key message I would also give is that we have abatement costs for one starting from 100 euros per ton CO2 up to 300 euro per ton CO2. So that's the range, and that brings us to get a level playing field with fossil fuels. In some sense, CO2 needs to become a price. So otherwise, there will just be some additional costs, and it will be difficult just from a price perspective. But that gives you a feeling. So in 2030, when this will be start, what would be additional costs? And clearly, there's a lot of discussion in politics how to handle that, how to get a level playing field. And that again, clearly, there shifts, and especially for hydrogen, the picture shifts again if you take in also the transport costs overseas. That's just an additional factor on that picture. So with that, I would like to hand over to Stefan, who would go more in detail how to use really those fuels and what are the options in the maritime industry. So thanks a lot for the moment.
So good morning and good afternoon always also from my side. Now my key takeaways from what Daniel said are, first of all, working towards CO2 neutrality is not a nice to do. It should be taken as a must do. And on the other side, I learned as well that there's different kind of fuels which support CO2 neutrality. And also we learned that these fuels might be available on a big scale in the future, and they might be somehow affordable as well. But definitely these fuels, they will have implications. Also in the marine industry, there will be implications from a commercial side, there will be implications from a technical side, there will be implications from operational side, also from safety side. And that's what I would like to talk about now, elaborate a little bit about these implications. Now with that slide, which we see here now at the moment, we see on the upper row, we see the different options of power to X fuels. Coming from the left side to the right hand side, we see on the left hand side, we have like the original energy coming from solar or wind power. And we just learned that we can convert that into electric power, and via electrolysis and synthesis, we can produce CO2 neutral fuels. So this is the energy carriers, and they can be used in the marine industry as well. But as I said, these different fuels, they have to be elaborated with regards to their implications to the marine industry. So we know that there's different energy converters available. So we can talk about battery systems to use the electric power we can see here on the left-hand side. If we go to the right-hand side, we understand that there's opportunities to transfer hydrogen into energy using fuel cells or using like hydrogen engines. We can convert these fuels now like into methane using gas engines or as well fuel cells, also in the marine industry. And going further to the right hand side, then we come to the liquid fuels like methanol, which we can also burn in a methanol engine, or we can also use methanol then later in a fuel cell. And on the right hand side, we then see like DME fuels, which are synthetic fuels which can be produced CO2 neutral, or even synthetic diesel, which comes very close to the existing diesel fuels, and this could be burned in a diesel engine. As I said, this has implications on the one hand side. With every step to the right hand side, it is quite clear that the energy efficiency will be reduced. So we have to use existing energy in order to convert these different kind of fuels. On the other side, going more to the right hand side, the compatibility with today's engine technology will increase. So the question is which kind of fuel to use and which is the implications there. One implication you can see here in this kind of diagram is the different fuels we are talking about, they have a pure technical implication. So the energy density will be affected by using these fuels. We see diesel, today's diesel, as a well-known fuel in the right upper corner of that diagram, showing the state of the art of today. On the x-axis, we see the gravimetric energy density in kilowatt hours per tons. And on the y-axis, we see the volumetric energy density in kilowatt hours per cubic meter. And one is for sure, these different fuels will have lower volumetric energy density and as well lower gravimetric energy density. So if we want to transport and use those fuels in the marine industry, there will an impact on how can we transport those fuels, what is the tank system we use, and what is the amount of energy we can transport, and then with that also use in a vessel. We see that there are some fuels which have a comparably high gravimetric energy density, like methane, which is liquefied. We see methanol as a fuel which has somewhere in the middle of this whole area gravimetric energy density, but as well volumetric energy density, which is considerably lower than today's diesel. So on the one hand side, we gain something with these CO2 neutral fuels. On the other side, we have to find out what the implications are and how can we use these fuels then in different maritime sectors. And with that, I come back to this fuel chain, which we discussed before. On the left-hand side, again, we have the electric power. We go via hydrogen to the right-hand side, methane, methanol, synthetic diesel, and now you can see on the right-hand side as well ammonia, which is an important fuel to be taken into account in the maritime industry as well. The second row shows us the different energy converters which we could use, like batteries, combustion engines, or fuel cells in order to burn these fuels and gain the propulsion and onboard power we need. And as I said before, there's different kind of implications. This diagram shall show us a little bit what we see as implications regarding technical issues, regarding commercial issues, regarding safety and operation as well of these different kind of fuels. And as I did before, I would now like to start with which is the technical implications which we have to consider here. And you can see with that diagram, this is our actual evaluation of those fuels with regards to the impact on weight, which we have to carry on a vessel, and system space, which must be found in a vessel as well. And the arrows you can see here is just saying there might be no or neglectable influence if we compare that kind of fuels and the energy carriers and converters to today's technology based on, let's say, diesel technology. There might be a significant influence or even a really high influence as well. And the evaluation is our today's evaluation. We are quite sure that this evaluation will change in the future. We will gain more insights, new insights, which will change this kind of evaluation. And so, as Daniel said before, the discussion with you, with all of the stakeholders in the maritime industry, these discussions we have to do, we have to intensify that in order to sharpen this picture and to really understand how can we make use of these opportunities, different kind of fuels, but also what is the implications. Now, second implication, I said before, there is this commercial implication, so we can talk about CapEx, what additional amount of money we have to invest to build a vessel based on these technologies. Also, the OPEX, so what is the money we have to spend during the operation of the vessel, has to be taken into account. And as one example, yes, we see that electric power might be with neglectable influence on the OPEX, so on the money we spend to operate a vessel. If we do that clever in some applications, this might be possible. There must be an additional amount of money spent in operations if we use hydrogen, either compressed or liquid. The same is valid also for other gases, fuels, or also methanol, synthetic diesel, or even ammonia. So quite clear, CO2 neutrality is not without increase of cost. That's what we have to take in account. The question is, how can we handle that in future? Can we handle that as individuals, or must there be global incentives to do that, to achieve this goal of CO2 neutrality? Next implication is safety, also very important. We believe that with the state of art of technology we have, providing battery-propelled pure electric vessels might be treated to be on the same safety level as we do with diesel today, because we have technology available and we know how to handle that. And this might be valid as well for different kind of fuels, like synthetic diesel. But we see using, for example, hydrogen or as well ammonia, the safety measures to be taken must increase. So this does not say with a lower safety value of ammonia should not be treated as a marine fuel. We just have to understand that ammonia is a harmful gas and we have to take care about that. So looking into operations at the end, what could be the achievable endurance of a vessel if we use the different fuels, and what would be like the charging time, which we have to take into account. And we understand using battery systems, the endurance from today's perspective will go down significantly, and the charging time depends on the charging technology, might be really high. Also, if we use like methanol, if we look into the energy density of these fuels, we talked about that before, the endurance will go down if we compare to today's diesel fuel. Also, the charging time might increase using these different kind of fuels, and we can handle that, but we must know that and we must take that into account. So if we talk about these implications, our learning is implementing these fuels and the energy converters into maritime industries, into the vehicles. We would say like electric power, we see there's a future of pure electric power on short routes with low energy demand. Using hydrogen or with methane, we can use them as well in the maritime industry. We would prefer to use those on short and medium routes. We can use as well hydrogen and fuel cells on long routes, but there's higher implication then. And we have to find out which is the best way to solve these challenges in the future. Methane, again, many segments can be treated with methane. We would not prefer to use that in small ships, like small yachts, for example. We might think more about methanol or diesel fuels, which we can use in a lot of maritime applications. As well, we see ammonia to be used in a lot of maritime applications, but we would prefer ammonia to be a fuel for deep sea shipping, not so much to be used in highly populated areas. With that said, I would like to come to an example of integration of these different kind of fuels and the energy converters into a typical vessel, which is a tugboat in this case. We used existing design of a tugboat with a length of 28 meter, width of 13 meter, which is equipped with a propulsion power of roughly 5,000 kW, 100 kVA of onboard power generation available. So it's a tugboat with roughly 75 tons of ballast. What does the integration study tell to us? So you see here 3 different variants which we looked for. On the left-hand side, you see the implications of driving the tugboat with a methanol system, which consists of two spark-ignited engines with e-methanol. They provide roughly 4,400 kW of propulsion power. In this case, we just used a study of two fuel cells to provide with roughly 1,000 kW of electric power, which we can use either on as a on-board power generation. As well, we can use that with a hybrid drive to support the operations of the vessel. The implications are quite considerable. First of all, we install like 100 tons of system into this vessel, but the methanol system gives us a high endurance. You can see the endurance number below here. This is 290 hours of endurance, which is being made available. In the middle area, we can see a battery system integrated into the same vessel. 140 batteries, of each of them containing of 7 modules, provide us with 5,400 kW, 11 megawatt hours of energy. The weight of this system is comparably low to the left-hand side, 64 tons. So why is a battery system even carrying less weight? It's quite simple. We also have an influence on the system space. So we are just not able to integrate more batteries and converter systems into the existing space than these 140 batteries at the moment, which gives us an endurance of 8 tons. So this clearly shows operating a tugboat based on these kind of battery system will considerably reduce endurance. And this has a high amount of influence on our operations. We have to take care about that. The fuel cell system on the right-hand side, it's a system of 24 fuel cells, each of them 200 kW. Again, we land at 4,800 kW of power here, 70 tanks of compressed hydrogen, 250 bars we use in this case. This ends up with 45 tons of system weight. And again, we are talking of low endurance in this case. And which says with a typical load profile of a tugboat, we will end up with an endurance of roughly 17 hours. This is our prognosis in this case. So very clear, we can install different kind of propulsion systems based on different e-fuels in this vessel, but it will have cost implications, it will have technical implications, and it will have operational implications. We do these kind of studies for a lot of different ship types to understand how can we do that and what is the implications. Is there a preferred system solution with regards to total cost of ownership, operations, and so on? This is what we are working on to make us more understand how we can use the different opportunities. And as I said before, it's extremely important that we discuss that with you as the stakeholders, shipbuilders, operators of the vessels at the end. Now, my last slide shall make a prognosis about how do we believe these different kind of technologies will make their way into different kind of applications. In the upper half, we see a study which we did for a mega yacht, 50 to roughly more than 100 meters. And we believe in the range of 2030, 2035, less than 50% of those vessels will be with conventional diesel systems. So that means that even in the next years, we will see that the traditional diesel propulsion will be supported by hybrid propulsion. This is already taking place today. So hybrid propulsion is a way forward in the mega yacht industry. And within 2030, we are quite sure that we will have the first fuel cells already being installed on mega yachts to support the auxiliary systems, so the onboard power generation. We will find hybrid technology based on probably some amount of power to X fuels, very clear within 2030. additional power sources like solar panels we will see in these kind of vessels as well. And in 2040, we believe fuel cells will make really a way forward as well in these kind of vessels. Really very much depending, of course, on the fuel infrastructure. This is something which has to be solved. Hybrid propulsion technology with power-to-X fuels, this is something that we will see in those mega yachts in the future. Looking into a fast ferry on the lower half of that picture, fast ferry in the range of 20 to 40 meters. Also here we see that less than 50% of the vessels will be propelled with conventional diesels in 2035. So we will go green in 2025 already. So we see the first vessels being propelled purely electric, short routes. We see that as well hybrid propulsion is used also in ferries, and the first pure E pilots are operating. LNG plays a role, maybe as a technology which will be used for the next years, and then we see that in 2030 we will have already more and more batteries replacing gensets. We will have fuel cells being made available for that industry as well, and power to X from our point of view will be available in these areas where those vessels will be operated, so that we can use power to X, the first power to X fuels in 2030 in ferries. And on the way to CO2 neutrality, we will see that there will be more and more fuel cells also being available, but as well combustion engines being available here to make power to X fuels being burned in those kind of vessels. So for us, it's quite clear that we will have to provide these energy converters. So we will provide solutions for the different applications, but we are sure that first of all, there will be different solutions for different applications, and we must find out the way to go forward. And with that, I would again hand over to Daniel. Thanks from my side.
Yeah, thank you, Stefan. Yeah, I think that might sound a bit partly, or not say to science fiction for somebody of you, or far away. And to close our presentation, I would like to give you the perspective. It's not far away for us as a maritime industry, for us at Rolls-Royce. So if you just take into account that the ship lasts up to 40 years, and if you want to have an impact in 2050, so we need to have commercial, available, CO2 neutral ships by 2030. And if you then go back, so maybe 2 years, when you have the order, start to build the ship, 3 years, 2027, when to start with the ship design, and especially for new technologies, we need to discuss securities, you define standards at all, also bring costs down. So easily up to 2025 for maybe not so complex technologies. I would guess 2033, if for example we talk on ammonia, so how do we get ammonia as a fuel and have all the required standards for that will take a bit longer. So if you just take 2033, 2025 in perspective, where we need some kind of decision, and like Stefan pointed out, there will be maybe not a single solution for everything, but at the end we believe we need some converging, because fuel requires an infrastructure, fuel requires a converter. So we as an industry, and everything needs to be integrated in a ship. So we as an industry have to work collaborative on that topic. So we need a converging, and by that we are now to 2020. It's clear and it's right that we need to assess, work on new technologies. We need to have inclusion of all stakeholders in the ecosystem to discuss this. So we are in a diverging phase. But I think important to know that's not, we're talking about 10 years now. So we see the time perspective of the next years where we need to assess that, but then we need come really to a converging phase at the end to have really commercial available ships by 2030. I think that gives the perspective that everything is not that far away before we need to take decisions what is the route to go. And therefore, I would like to come to the summary. So from our perspective, it's clear that we really need to have the full picture. So we need to start with the fuel origin, the energy source, and that's the key at the end for climate neutrality. Electrification of fuels is, I would say, one key element of getting the maritime shipping to climate neutrality, because it addresses existing fleets, it can use existing infrastructures, also, and it enables worldwide energy harvesting. So, which then at the end is the basis for getting the fuel, amount of fuel which is needed for amount of energy. The propulsion technology is clearly an enabler to use the climate neutral fuels, even especially when we talk about new fuels like hydrogen, ammonia or methanol. And probably marine will always depend on energy dense fuels. It needs to be not liquid. We have already LNG, which at the end it's a liquefied gaseous fuel, but that's one key element, that we need a high energy density for most applications. And the good message is we believe e-fuels will become competitive with biofuels. They will stay in the coming, what we see in the coming years, more expensive than fossil fuels. And all will depend, and that's something we believe there will be not a free market evaluation with e-fuels. We need a suitable regulatory framework. So really topics which are discussed like CO2 price, regulatory requirements we have in different countries, they will play a major role, how the market uptake and how fast the market uptake can take place. And at the end, and that's partly we need to accept, or we need to embrace, and we will have multiple propulsion concepts. There will be not like a single concept, and we see that already, for example, the upcoming LNG, and they will coexist in the future and depend really on the application which to use. By that, I would like to thank you for your attention. We have fortunately time for a few questions. And also I want to make you aware that you can download the presentation via that link. And yeah, with that, I'm happy to answer some of the questions already out of the chat together with Stefan. So therefore I ask now the team. Next. Okay, yeah, there's one question from Fabio Buturi. The question is, why can't HVO and synthetic fuel be the philosopher's stone on the next decade? They are the only form of transition that reduce CO2, NOx, and PM emission, fostering an economy of a global scale. Yeah, we would agree on that. In that sense that because those types of fuel that can directly use direct infrastructure and fleet. So that's clearly the benefit. But if you just take into account the CO2 you need for that, for example, maritime and aviation fuel, because aviation is maybe the other sector would need like e-kerosene. You need roughly 40% of the CO2 which is emitted today by the cement industry. So the question is really how, if you take all the sectors into account, do we have enough CO2? Therefore, we believe if we take all the sectors, there is a need and a room for new fuels, which, for example, that's why hydrogen is very attractive, where you don't need the CO2, and other where you need that, where the argument is more on the side addressing the existing fleet, where you need the CO2. So there's really the question, how do you get in a CO2 neutral way access to CO2? So therefore it will be both, and therefore we believe we need also on the longer time range we need to be also have a look on other fuels we don't know today. Okay, okay, and maybe because one additional mark, maybe HVO. I mean, there are two routes. So HVO, it's bio. The main route you get it today, it's from biogenic sources, and that's not completely CO2 neutral. And from our projection, also to let's say at the end use the complete amount by biofuels, as mentioned already. That's from a sustainable perspective, maybe not the right way to go. So let me think. There's another question. Would the hydrogen have to be converted close to the wind power source to avoid having transport hydrogen to existing infrastructure? I think that's a very good question. And we believe also, especially in the ramp-up phase, and I know a lot of other stakeholders have the same opinion, we will see the fuel produced locally also where the use of the fuel is. So that's one way, because we have not the infrastructure. In the longer range, especially for hydrogen, we believe we need to build up an infrastructure, because clearly it makes also more from an efficiency standpoint sense to have the for example, the electrolyzer close to the wind turbine. Even what's more important, have the synthesis close to the CO2 source, because that's one cost factor, to have a concentrated CO2 source. So different aspects, but we would agree that in the first phase it makes sense, because we have not the infrastructure to have the electrolyzer close to the usage. Okay, let me check. There's one question, what are the most promising regions to harvest renewable energy, produce hydrogen? Yeah, maybe can refer to that heat map I showed. So that's, yeah, clearly Patagonia for wind, for example, Chile as a whole, and then clearly Middle East, Africa, Australia is very interesting, Scandinavia, especially with water. I think at the end that is one aspect we need to consider, and that there are some studies already going on in that region. Where is the, let's say, from just energy perspective, a good location, and also maybe from economic more stability side. But overall, I think the interesting thing is that we have now much more regions which can put, or new regions which can benefit in that economy. So just comparing where we get our oil today, I think that makes it on a global scale very attractive. Okay. Yeah, there's another question. As far as I know, all synthetic e-fuels require hydrogen for the synthesis process. For ammonia, however, there exists also a lithium cycling electrification strategy that's said to work without requiring hydrogen. Is ammonia the only fuel that can be produced without hydrogen? Yeah, we believe that there are a lot of promising ideas to have alternative ways to do that, but also regarding the hydrogen production process, that there are a lot of alternatives combined to electrolyzers, but there are let's say that they are in the fundamental research stage. Also methanol, there would be option. Let's say why we put that hydrogen electrolysis route in the focus is because the technology for that is basically there. There's additional potential for further improvement, efficiency, but here we have the technology, and the challenge is now more to scale up. And therefore, we believe that will be or needs to be the first step, because we need to scale up to come as soon as possible to a larger scale of plants. But I mean, if we go in that, let's say, CO2 neutral economy, I'm sure there will be space, and if you look to 2050 and beyond, for other, let's say, alternative and maybe more new ways. That's clear. But really the start, just from looking what technology is already mature enough, we believe is really that idolizes synthetic synthesis route. So at the moment, at least I have not seen another question. There was another question mit am Ende. So just my Tag team. Okay,
Gentlemen, do you still have another question? I didn't want to interrupt.
Maybe just answer as a last question. How far is M2 in developing a methanol-fueled engine for marine use? I think you have seen that we consider methanol of the, let's say, interesting upcoming options. Clearly, methanol would be a new fuel. I mean, it has some basic infrastructure. Therefore, we're looking into methanol combustion already. And there's also a public funded project, MassQuest, if you would like, you can research that. And so that was publicly available. You can have a look in that. So yeah, we're working on that. For us, clearly, the interesting question is in what time scale will the methanol market evolve? And so that's then for us also the point when we really will bring a product. But we work on that because I think we showed that we believe it's one of the upcoming but new alternatives. But really, I think the diesel route is or the e-diesel route, maybe the route which has the larger potential on a shorter time scale. So with that, and I was informed time is over. If there are more questions also in the chat, we will answer them in advance. And you can also you see the contact dates of Stefan and myself. You can contact us. You can so we can also follow that. You can contact also our central departments on that. So with that, I would like to thank you again from our side and to hand over to Mrs. Lauer.
Yeah, thank you very much to our speakers of today, and of course also to our participants and their questions. We hope you enjoyed our Ship and Offshore webinar powered by MTU. I thought it was really some interesting information about the future of shipping and a decarbonized industry. So as I mentioned at the beginning, there will be an email with a link to the recorded webinar and also another link where you can actually find the presentation of today, because I think that was asked a couple of times. And again, any questions that were not answered today, because I think there were some, will be addressed in the following days. So with that, thanks everyone, take care and goodbye.
Thank you. Goodbye.